Good evening, everyone. Today we'll be conducting the week 10 session for this digital control and switchboard power converters and FPGA based prototyping. And this course has been conducted by Dr. Santanu Kapit, and I'll the TA for your problem solving and doubt clearing session. So we'll begin. So the outline for today is I'll be talking about voltage based constant on time control. Then we will talk about what are the various. First, we will try to understand how we implement constant on time control voltage based. Then the FPGA implementation, the codes for each and every module. We will understand those codes, and also some hardware research which sir has demonstrated that we'll just see some images of that. Then I'll be discussing about mixed signal constant on time control, how we add current mode control, and we use the same old module also. We just have to make certain few changes. Then we'll also consider about how there is changes in stability for fixed frequency and variable frequency. Why in certain cases variable frequency is advantageous, how it has that inherent current flow stability, etc. We will look into that. Then also I'll be talking about this adaptive constant on time control, where the on time is adapted based on some peak reference. Okay. So we'll start with voltage based constant on time control. So this is the normal diagram. This is your normal diagram for a buck converter. And we want to do we want to do constant on time control. So what do you mean by constant on time? Can anyone tell?
On time will be constant, but the frequency, this is the variable frequency control. Your off time will be varied. There will be some minimum off time.
Okay.
Based on which the pulse will be changed.
Yes. So this is my buck converter. QH is my main switch. It's the active switch. QL is the complementary of QH with certain dead time. Okay. Now, sir has demonstrated constant on time control, and that is for light load condition. Okay, we'll go into that later. First, we'll understand what is constant on time control. So this is my fixed on time. Okay, this is my fixed on time. That is off for some duration. T off, and then again it will turn on and off. Okay. So this on time is fixed. Okay, this on time is fixed. This off time changes depending on your controller and when it gets triggered. Okay, there is a minimum off time. Okay, there is some time which is known as your T off minimum. So, and in that minimum time, any signal which comes to turn it on this timer, it is disregarded. It is not considered. So we have a fixed on time. After that, we have a minimum off time, and then only we can turn on the timer, or else it will have to be switched off. There is no, it should not be turned on for that time. So how we do? We have NREF, which corresponds to VREF. Okay, and this is your V feedback is actually your signal from your output voltage is coming from a V feedback, and that is passed through a ADC. This could be implemented using an analog comparator also, but in the case which sir has shown, it is being implemented using a digital comparator. A digital comparator which is occurring inside the FPGA, and you just subtract them, and you will know based on the sign of the MSB of the subtracted value, you will know whether what is greater, what is smaller. Okay, so this is your VREF and this is your ADC data. If your VREF, so you see this is the output voltage curve. Okay, let's draw the curve over here. This is my Vref. When my output voltage goes below Vref, okay, that time a trigger signal is generated and turns on this timer. And then it will turn on. And then it will be on for some duration. Then it turns off. Okay, at this time, it has turned off. So it has to be off for some minimum off time. And then it keeps on falling, falling, falling. And then once it goes below this Vref again, over here, then it will generate another trigger signal. And that will again turn it on. Turn it on for a fixed duration. Okay. So this is how voltage-based constant on-time control is implemented. So this signal, when this output voltage goes below your Vref, that signal is known as that signal comes in the form of QTR, okay, QTR. And when the rising edge, when you see QTR is rising, then it means I have to turn on the timer and it will be on for a fixed duration. That's why it is positive edge. Positive edge means at the rising edge. Okay, at the rising edge of this trigger signal, then we will turn on this timer. All right. So after this, after it has been on, there is a minimum off time also. The minimum off time also will be checked. The timer, monoshaft timer is on for a fixed duration. Then Q comes, and then with a suitable dead time, we give QL and QH is generated from that. All right. So this is basically the understanding of constant on-time control using voltage-based control. Next, how are we implement? Does anyone have any doubts in this? Monoshaft timer means it is once triggered, it will continue to count. The timer will continue to count, and only after it finishes counting for that duration, then only it will accept the next triggers. Okay, so while it is counting in between, like over here, just suppose over here one signal comes, it has to ignore that. Okay, that's why it is monoshaft timer. Now, how will we
Sir,
implement?
this waveform,
Yes.
this one which you have drawn is the Q waveform, right? The small Q.
Yes, yes. This one. Yeah. Then afterwards you add your dead time and correspondingly you get QH and QL.
Sir, why there is a feedback from Q to minimum off time?
Why there's a feedback from Q to minimum off time? Like when, depending on the state of Q, we need to know whether it can be triggered or not triggered. So we will actually go into the block diagram of the FPGA based implementation and then you'll be able to understand. So why both you need your on time logic as well as your minimum off time logic, both should be considered and then you generate Q. Okay, and then you will generate Q. Both have to be considered in that case. All right. And any other queries?
See, whenever the positive edge reduction comes,
Yes, yes, yes.
sir, whenever the positive edge reduction in QTR comes, it should be fed to bonus of timer directly.
Okay, like the implementation we'll have to see how it is done in the FPGA. We'll have to check that. Why this minimum off time? This is actually just a representation. How exactly in the implementation we'll get a clearer understanding. Right? Any other queries? Okay, so I'll proceed further. So to implement this, we have a constant of VMC. This is our main module. It will generate high side, low side, these gate signals. Q load is for transient, which is ignored. This for low transient. This is for certain transient we can give, but they are not considered over here. F clock is the clock signal. This is the high frequency clock signal. And also we have a FADC. This is the clock signal for driving the tag, for triggering the, for running the ADC, you need these some certain clock signal for the ADC. Then V feedback is the signal from your output voltage, sensed output voltage, and that gets converted to ADC data, which is 10-bit ADC data. Okay, so this is the FPGA main module, and we have a constant order modulator is present. So it has an enable block, N timer, N minimum. N minimum stands for N timer stands for your fixed on time. Okay, this is your main T on. N minimum stands for your T off minimum. Okay, F clock is your high frequency clock for running this modulator, and Q out and Q finish. So Q out is this. Okay, this is your Q out. Your T on, just constant. Then after that, there's a small T off minimum. Okay, that is there. And once your on time and your off time is left, then there's a Q finish signal comes in. Okay, Q finish, it's like a sort of flag is there. That signifies that now it can accept other enable signals which can trigger your constant on time modulator. Okay. Okay. So this is the main implementation diagram for you to understand how we are implementing the constant on time, how we are implementing constant on time, how we are implementing minimum off time. So enable signal is like your set pulse, okay, to set your output high. Similarly, and then Q out temp. There's also Q out temp 1. So this is for your minimum off time logic. So both minimum off time as well as your constant on time, both are considered to generate the actual output signal, which like this curve. Okay, this curve is generated from that. Then Q finish is the one I told after your minimum off time. Then you generate this Q finish. Okay. So there's a clock generator module, the constant order modulator, etc. Also a clock manager. We want to implement this edge detection. If you see over here, we have this edge detector. Okay, this positive edge detection. So to implement this also, we have an edge detection circuit. So that is there in the clock manager. Okay. So now we will go to the main module. So this is my main module, constant on time VMC. It takes many inputs. It takes a clock. Also, there's a ADC clock is there, PWM high, low, ADC data, etc. My input signal is my clock. This is my high frequency clock. Now your output signal generated is a ADC clock, QH, QL. Okay, these are these. Then my input also is a ADC data, just a 10-bit ADC data, which is in the form of Q1.9 format. If you remember in previous implementation things, we had considered that the ADC is generating data in the Q1.9 format. Next, and it is signed format. Okay, another we are defining a register com underscore status. That is the status of my comparator. Then there are certain buyers Q out, QF, Q enable, F external, and we will use them. So then certain parameters are defined. N underscore timer. So what does N underscore timer mean? It is corresponds to 200, and that signifies that, and that is used for generating your on time. Okay. If I want to change my on time, then I have to change this N time. So this value over here, okay, this value over here will change my on time. So if my on time earlier, suppose it was 1 microsecond. Okay, now I want to double it. Okay, so I will just multiply by 2, etc. Then I'll make it 2 microseconds. So whatever changes in on time I want to do, I have to vary this parameter. This nmin parameter stands for my minimum off time. Okay, it stands for my minimum off time. T of underscore minimum. Okay, nmin stands for that. Nref stands for my output. We are doing, there's a reference, right? There's a reference vref and your D output. Okay, so this vref is corresponding to it. We have a nref, and then this is your digital comparator, which is inside your FPGA. Okay, so any doubts still here?
Sir,
Yeah.
sir, in this on time, if suppose initially we are having 1 microsecond, this is now at 200.
Okay.
If we want to increase to 2 microsecond, then it has to be increased to 400, right?
Yes, 400. Yeah. See, how is your on time being generated? This is my on time. Okay. It is being generated by a counter. Just counting. Okay. When this counter reaches, okay, just consider this. When it reaches its maximum value, say 200. Okay. Then your counter gets reset, and this also goes down. So this is how this on time is counted. So to implement it, we have to give clock signals. Okay, these clock signals has to be given. So if my maximum value is 200, in 200 into t clock, my counter will be high. Okay, and this will be high. But if I make this a value 400, then the time will be 400 into t clock. Yes.
Sir, actually, sir, how will the FPGA will recognize that if you give 200 here, it will take on time of 1 microsecond? In the program we are writing like this.
Okay, but no.
In this n bit.
Yes, understood. This is what I understand is your doubt. Assume over here t on is 200 into t clock. Okay. Now, in the hardware board which has been used for this course in the demonstration, your clock is of 100 megahertz. Okay, 100 megahertz. So the t clock will be 10 nanosecond. Okay, 10 nanosecond. So if you do 200 into t clock, 210 nanosecond, you will get 2 microseconds. Now,
so by calculating that, we are writing this.
Yes, by calculating that, we are writing this. Now, this F clock is an external signal, external clock signal which you are providing for the FPGA. That depends on the crystal which you choose, or whether the crystal is already available. For that particular FPGA board, you'll have to see what is the clock frequency. Based on the clock frequency, you will decide how many ticks or how many increments of that clock I require to increment my counter. So over here, I realize I need 200 of those to get my on time of 2 microseconds. So this has to be used and this has to be used, and then you will calculate this value. Similarly, for the minimum off time also, you follow that same procedure. How will you decide how much parameter value you want to give? So now
in this case, we are keeping the reference to be 0.25.
Where?
The reference you are keeping at 0.25. Sir.
You'll have to calculate, it will be 0.25 and some small value. Yeah, some small value, around 0.25.
Oh,
yes.
one. Okay.
That one will be there. Okay. So then all these the clock generator, COT modulator, clock manager, all these are initialized. Okay, these all are initialized over here. Now we will go to the module for clock generation. So this clock generation module has been taught in previous things also, but we will go into it. How, what actually is this clock generation? I told my F clock. Okay, F clock is of 100 megahertz. Yeah? My T clock is 10 nanoseconds. Now I have counter 1, counter 2. This is NADC's 3. So what happens is, we'll consider for the ADC clock, okay? Just for the ADC clock. How it is generated. It is first 0, then it goes to 1, then it goes to 2, then it goes to 3. So this is 0, 1, 2, 3. And then it comes back over here. Again goes to 0, 1, 2, 3. Okay. And this is my T clock, my F clock. F clock keeps coming at over here, 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 here. So when the clock, okay, so just consider from here. A clock signal comes, it goes from 0 to 1. Another clock signal comes, it goes from 1 to 2. Another clock signal comes, it goes from 2 to 3. Then the next clock signal comes, it resets it, because I have told the limit is NADC is equal to 3. So maximum value it will go to 3. Once it reaches 3, it goes back to 0. So effectively, my time period is 4 into T clock. Okay. So effectively, my ADC clock. Okay, and this is my ADC clock. From here, I will get my ADC clock. Will be this. Okay, my ADC clock will be like this. So this time is my time for my ADC. It's my time for my ADC clock. No, I made a mistake. 1 minute. So this is my F clock, and my ADC clock, which will come out, will be like this. It will be 0 here, it will be on, and then over here again, it will come. So this clock is my FADC clock. Okay, and the time it takes periodically to be generated. Okay, over here also it will, let us consider over here also it will go high, right? So this time, okay, this time is 4 into T clock. And this is my time for my ADC clock. So you see T ADC clock is 4 into T clock. So my 1 upon F ADC clock is 4 upon F clock. So my F ADC clock is in actual reality F clock upon 4. So if my F clock was 100 megahertz, my F ADC clock is of 25 megahertz. So is this point clear?
Yes, sir.
Similarly, I have a switching frequency clock also. That is 499. So similarly, you have to do 100 divided by 500. That comes out to be 200 kilohertz. Okay, so that is another clock signal. So this is my switching frequency clock. This is used as an external clock, and it generates a clock of 200 kilohertz. This is the code, and this is the code for my ADC
Sir,
clock.
this
Yes, yes, tell.
the FADC clock.
No, FADC clock, yes.
Sir, when that 4 into 3 clock. Sir, when it comes, when the pulse comes, Sir, this conversion will start to happen, right, sir?
Yes, yes, correct, correct. Conversion of the ADC, right?
Yes.
Yes, okay.
Oh, that conversion is only reflecting as a step waveform. 1, 2, 3.
No, 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 no. You have see this. This is just generating a clock signal. Okay, this is a clock signal being generated by the FPGA. Now this clock signal will go to the ADC. This is my ADC. It will get a clock of FADC, and this clock of FADC comes from your FPGA. Right now, what I'm talking ADC and DAC clock. This is how to generate this clock. I'm talking about how to generate this clock. I'm not talking about the ADC. Okay.
No, sir. Yeah, that's okay. Sir, if this clock comes, this FADC comes, whenever the pulse of FADC comes, for every 4 clock cycle,
yes,
sir, this ADC will start to convert, right?
Yes, it will start to convert.
The conversion of ADC will happen.
Yes.
It will convert for 4 clock cycles and again.
No, that is a different thing.
No.
Yes, I'll
okay. Sir, if
tell.
Sir, between one ADC pulse and the next ADC pulse, what will happen at the ADC, sir? Okay. So this is my analog signal. Okay. This is my digital signal. Okay. Now, okay. And the ADC clock comes like this. Okay. After every yes, just assume no 4, 5, whatever. Just see, this is of 25 megahertz. So let us say how many 25 megahertz is corresponds to what's the frequency around some 40 microsecond micro. Or just 40 nanosecond. Okay. So this is 40 nanosecond. This is my FADC clock. Once this clock comes here, ADC, the clock comes over here. Okay, assume the value over here was this analog signal. Okay, this is my analog signal. Let me draw more. Here. Okay, assume this analog signal has a okay. This is actually analog, so it will be continuous. Yeah, the analog will be sampled at this frequency. Yes, it will be sampled at the frequency, but there's a delay of 6 cycles. 6 cycles delay is there. So suppose the value over here at this instant of this analog signal was 5. Okay. Then at this, okay, suppose it was 5.1. Okay. Then after, like, this is the 0 instant. Then 1, 2, 3, 4, 5, 6. At this time, at the 6th ADC clock cycle, then I will get 5.1 in terms of digital. Okay. So this is my delay. This is my ADC delay. This is my conversion delay. The ADC conversion delay. Okay. So what is being done is 5.1 is here. Suppose over here it is 5.2. Then at the next clock, at this clock, you will get 5.2. 7th clock. At the 7th clock. So what is happening is we are continuously triggering the ADC. Okay, we are continuously triggering the ADC. It is sampling and all, but to convert it, it is taking 6 cycles. And why this is happening is it is a pipeline ADC. It is a pipeline ADC. It has some high throughput and all that certain stuff. So what you must remember is you take a sample at this instant, you will get the value at this instant. Again over here, I'm taking a sample, I will get the value after 6 cycles. Again over here, I take a value 5.3 assume, I will get the value after another 6 cycles. So there's a delay of 6 cycles. And I need to give these clocks, these ADC clock signal for the ADC to operate. Okay, the ADC to function, even your laptop to function, it has certain clock signals are coming to it. So similarly, for your ADC to function, you have to give a clock signal. Okay, so these are those clock signals, and we are continuously taking samples of the analog value, and that digital value is being reflected at the output after 6 clock cycles. Okay, to understand more about what is happening internally, you'll have to understand the operation of the pipeline ADC, because the ADC being used as a pipeline ADC.
So this delay specification we'll be finding in the ADC data.
ADC in the ADC, it's there in the ADC data sheet actually. We had shown also in week 6 or week 7 about the ADC DAC driver. That time it was shown.
That successive approximation.
Not
the different types of ADC.
There are different types of ADCs. Also, the ADC data sheet also we had spoken a little bit about that. So in that it was given that there are 6 cycles are required for the ADC to complete conversion of the sampled signal. Okay.
Sir, will this delay won't be in other ADCs?
It will be then other ADCs also. So we have to see the ADC.
Okay. Okay.
So now we have generated ADC and DAC plot. Okay, 4 into T clock is for my ADC. It's the okay.
Sir, our last program, our last set of code is for generating this ADC, FADC.
Yeah, generating the FADC. Yes. Okay. Sanjay is asking a doubt. Why 4 into T clock? So this is my F clock. Okay, 2, 3, 4, 5, 6, 7, 8, 9, etc. So this is my F clock. So you require 4 of this F clock to generate 1 clock of my ADC. So it is basically like a frequency divider. It's operating like a frequency divider. Okay. Yes. That's what I'm saying. No. My F clock. Okay. Okay, we'll proceed. So this is how from F clock we are generating FADC. So this is the code for that. Now we will proceed to the constant on-time modulator. This is the block diagram, functional block diagram for you to understand. So this is a free running counter. So what is a free running counter? It has 2 things. It has a F clock and it has a reset. If your reset is 1, then your end count value should be equal to 0. If your reset is 0, then your end count value will remain at the value of end count. Okay. Then when reset is 0 and you get a clock signal, okay, my clock signal comes like this. This is my F clock. Okay, this is my F clock. So when this signal comes, okay, when this F clock signal comes, then you must increment the value of your counter. Okay. So there are 2 things. If my reset is 1, no matter if my F clock comes, even if F clock comes, it will maintain the value of end count to be 0. But if my reset is 0, it will either hold the value of end count to remain as end count, and when my clock signal comes, it will increment the value of end count. So that is a free running counter, and it will be like this. Okay, assume it will go like this, then it's like this, continues to be like this. So this is for reset. Okay, your reset signal is like this. Okay, this is your F clock. F clock signal comes over here. Similarly, over here. Similarly, comes over here. Over here. Okay, it's not up to scale, but I guess hope you will understand. Then over here also, F clock will still come. F clock will again come. It will again come, but because my reset is 1, and here it was 0. So whenever F clock comes, it will increment. It will go 1, 2, 3, 4, 5, etc. When the reset has become 1, it goes to the value 0. And even though my F clock signals are coming, it will not increment the time. So this is the operation of a free running counter. Okay. Any queries in this? Because this is the basic functional block. So now you just told when F clock comes and your reset clock comes. Now your F clock is coming from your crystal, FPGA crystal, that is of 100 megahertz. It is coming periodically at 100 megahertz frequency. But who generates this reset signal? Who generates this reset signal? So we have given a logic. In my logic, what is my logic? If my n count, okay, this n count, this value, okay, this 4, 5 value, etc. If that value will exceed my n time, okay, suppose my n timer in this case is 5. This is my n timer, okay. This is my n timer, which is value of 5. No, let us keep n timer to be value of 4 because it is going greater than or equal to it. Okay, greater than or equal to it. So if my n count becomes equal to 5, okay, so then it is either greater than or equal to 5, then my reset will go high. Okay. So actually this meeting will end in 1 minute. So then this meeting will end and I will again rejoin. I will again start a meeting and you guys have to rejoin.
So end timer, we are fixing the on time. That's all.
Yes. End timer is fixing the on time. Yes, exactly. So this is the concept of your free running counter and how it is generated. So this sets my limit. Okay, this will generate when I will reset. So if my end timer is in source code, end timer is 200. So when your end count reaches 200, then a reset signal will come. A reset signal will come, and that will reset your counter. That will come over here. Okay. And this is your Q out temp. Okay, Q out temp is there. If this Q out temp is 0, then this value will be 1, and this also is 1, then reset will come 1, and your end count will take the value 0. Okay, so this is like a step-by-step procedure. So first I told the concept of your free running counter. What is a free running counter? Now we can look into the enable tree. So in constant on time, what we have? Okay, we'll go step by step. We have to see it. So this is your the whole entire screen is visible to you guys, right? So anything getting obstructed or blocked?
No, sir, it is visible.
Okay. So this is my model of constant on time modulator. This is the inputs and these are the outputs. Okay, and we have defined them. Inputs we have defined. There is just 1 bit. These are 10-bit inputs. This is just single bit outputs, and that you can see it from your diagram. Okay, enable is the input. F block is the input. We also have to pass in the value n timer and n minimum. Okay, these values also we are passing. All right. Then certain registers are made. Okay, these are registers. N count and n count min. That is this and this. So these are the outputs of your counter. It will start at 0 and it will go. This will start at 0 and it will reach to n minimum maximum. Okay, this will start at 0 and it will reach at n timer maximum. Okay, and that is implemented at a frequency of f clock. And that also depends on reset. If reset is high, then it will not increment. But if reset is 0, low, then it will increment. So these are conditions which I've put. And those conditions are written in the code. Okay, so this is just a block diagram for you to understand the code, but the code is implemented based on those conditions. Now there's an enable. Okay, this is a SR latch. So you guys know SR latch. How does SR latch work? SR latch, truth table of SR latch is if it is reset is 1. Okay, and we will consider it as a reset dominant latch. So even if X is 0, even if S is 0 or 1, your output Q will be 0. Okay, it will be 0. if S is if reset is 0 and S also 0, then it will hold the QOM, the previous value, which was 2. But if your set is 1 and your reset is 0, then Q will take the value of 1. Okay, so this is my truth table of my SR latch. Okay, the truth table of my SR latch. Now, set. Okay, this set pulse. If my reset is 0 and I give an enable signal over here, okay, I given an enable signal, then this Q out temp will take a value 1. So that is given over here. So always at the positive edge of enable or positive edge of reset. This is a conditional statement, and either at the positive edge of enable or at the positive edge of reset, I will go into this block, into this code. This if reset, what does it mean? If my reset is equal to 1, that is if my reset is high, then what? If my reset is high, what do I have to do? This free running counter has to be, end count has to be, no, it's about this, sorry, it's about this, we're implementing this. So if my reset is 1, what I have to do? Q out temp has to take the value 0. Okay, Q out temp has to take the value 0. Else, the next condition is, why has this come? Why have we entered into this? It is because either my enable was 1 or my reset was 1 or both were 1. Okay, there are 3 conditions. We are enable and reset. Okay, this can be 1, this could be 0, this could be 0, this could be 1, or both were 1. In this case, I am going to enter into this. So first it will check if my reset is 1, if it is these cases, what it will give? Q out temp will take the value of 0. And in the next case, else, what does else imply? It means that my reset was 0 and my enable was 1. Then I have to give the value of Q out temp has to take the value of 1. Okay, Q out temp takes the value of 1. So this block of code is implementing your SR latch or your SR flip-flop, which is reset dominated. Okay, reset dominates. If your reset is 1, no matter what input comes at S, we don't care. X stands for don't care. So irrespective of S being 0 or 1, if my reset is 1, my Q will be 0. Okay, so that is a reset dominated SR flip-flop. So we have discussed how this logic is implemented in the FPGA code, Verilog code. Now we will proceed to the next thing. Yes.
Sir, suppose here both the reset and this enable is there.
If both reset and S
That
is
is
there.
S.
So
SR is 1-1.
SR is 1-1. Your Q will still be 0. Okay. Because it will first check when once it goes over here, it will first check. If reset is 1, it will make the value 0 and it will not go into this. That is how we are making it reset dominant. So if my reset is 1, irrespective of S being 0 or 1, my Q will be take the value 0. Okay.
So yes. So in this case, when R is given higher priority, yeah.
Yeah. Yes. It is dominating.
Actually, they'll say if 1-1 comes, it is indeterminate.
What?
Usually, if S and R are 1, they will say in our VTech, they will say indeterminate state.
Yeah.
They will put. Okay.
Yeah, you could say you don't know what the output will be, but over here we have written the code. It is reset dominated. See, you don't
code is written in that way.
Yes, the code is written that way. See, you don't want any logical block for which you don't know what the output will be. See, input can come, any input can come. But that doesn't mean if some random input comes, like I should not know the behavior of my code. You have to write it in a sort of structured manner, right? Taking into conditions of all sorts of inputs coming to you, right? So an SR latches and SR flip-flops, it is either set dominated or reset dominated. That is there.
Here, but
Probably,
in this
Sir,
code, we have written positive enable or positive edge reset.
yes. So when the edge of
Here,
enable or
if,
reset
so,
comes,
so there is
yes,
okay. Here there is a possibility that both the enable and reset can be one as per the code,
yes, exactly.
but the output will be reset dominated.
Yes, yeah.
sir, what if I consider like enable like S dominated flip flop?
No, that you can consider, but that depends on your application. In our application, we are finding that
Like,
it's
but
reset
sir,
dominated.
in the
Yes.
thesis, it is given that something gonna miss in constant on time and off time.
In which thesis?
Like I gone through one of the references defined in the lectures.
Okay. Okay. What was it in
There
there?
it was. I'm not. What is written is like for one case it is set dominated, and for another case it is reset dominated. Like for constant on time and I am not clear with the exact architecture,
Mm-hmm.
but there will be some problems like some duty gonna miss or something else there gonna be.
Sir,
Yes, yes. Wait. Alpha set is
sir,
Banerjee
here
step.
you are saying reset dominated because it is if RST, right? That is why
Yes,
you are
because
saying reset
yes,
dominated.
yes, yes. If RST, that's
So
why
if you write if enable, then
it will be set dominated. Okay, but in our particular application, we want it to be reset dominated. Banerjee, I don't know exactly which architecture you're referring to, but it might be. In our case, for constant on time modulation, we want it to be reset dominated, and based on that, we have written the
Okay,
code.
sir.
Okay.
Okay.
So now we will proceed. Okay. So this is my code. Okay, now my another thing is for my counter. Okay, how am I implementing my counter? The reset. Now we will look at reset. Reset has two things. It is either coming from here. This is small RST. This is capital RST. Right. So this capital RST is the small RST. Let us say this RST is your small RST and Q out temp bar. Okay, it is inverted. Okay. So now, if my Q out temp bar, okay, this is tilde Q out temp means if my Q out temp was 0, okay, if my Q out temp was 0, then this will take the value 1. Okay, this will take the value 1, and then I will enter into this code. So if my Q out temp had the value 0, then I will implement where is this line of code. Okay, this line of code when Q out temp takes the value 0. Okay, I will implement this. I will give n count to give the value 0 and reset. This reset also will have the value 0. I'm assigning that value. Then, else if my n count, that is this n count is greater than or equal to n timer, then what's the condition? In that condition, what I have to do? I should make reset to be equal to 1 and n count, I must assign it the value 0. So it is this condition. Okay, reset, I give the value 1, n count, I will give the value 0. Okay. These are non-blocking statements, so they occur simultaneously. Okay, they will occur simultaneously. Then it will end. Else, okay, if either this condition fails and this condition also fails, then what does it signify? It signifies my Q out temp has the value 1 and my Q out temp has the value 1 and my reset, small reset has the value 0. Okay, this happens when my Q out temp has the value 1 and my reset is equal to 0. Then what I will do, no, and this means, wait a minute, this means my n count is less than n timer. in this situation, I will give the value of n count, I will increment it by 1, and at the same time, this reset will hold the value 0. Okay, it will take the value 0. So this line of code, this set of code implements my free running counter. Okay. Any doubts in this? So then no doubts, I'll proceed. And this is implementing my constant on time. Okay, this is for my constant on time block. Similarly, we have the same logic. Okay, another set of logic for minimum off time. Now this reset over here comes as a set pulse for my minimum off time logic. Why? Because this is my on time. Okay, this is my T on. Then when my reset becomes 1, that means my on time has completed and it will turn off. Okay, it falls and turns off. Then I have to start this count. Okay, that means I will give set over here, and set in the sense is I am sort of starting this count. Then it will count, and then it will hold a value for T of minimum. Okay, T of minimum that is determined by this n minimum. Okay, and further it will go out, the logic comes. Okay, so now how is this Q out temp 1 generated? Okay, how is Q out temp 1 generated? If my reset 1, what do you mean by reset 1? If this is high, then it will Q out temp 1 will take a value 0, or else Q out temp 1 will take value 1. So this is implementing my SR flip flop. Okay, same. It is reset dominated again, and now the reset signal is coming from here. In the previous case, the set signal was coming from the enable signal. Okay, this is my enable signal. But in this case, the set signal is coming from this previous reset signal. Okay, so what is constant on time control? You have a constant on time T on, but who starts this? There's an enable signal which comes over here. This enable signal comes over here, and this sets it, and then the counter starts running, and it counts. Then it reaches this end timer value, and then it gets reset. Once it gets reset, okay, it has gotten reset. Then when it gets reset, you get a high pulse. Okay, you get a high pulse. This is my reset pulse. When this reset pulse comes, what happens? This counter will start running. If this counter will start running, and it will run for a minimum of time, T of minimum. Okay, it will start counting. And when that minimum of time is over, okay, then it will give Q finish. It will generate this Q finish. Okay. Then when my next enable signal will come, then it will again turn on. Alright. So this is a bit complicated, but please tell your doubts.
Sir, when this Q finish comes, then Q out temp will be 0. So
Yeah.
after the NOT gate, it will be 1. After the NOT gate, it will be 1. So the Q out will come to know that the time period is over.
No, this is my Q out. My Q out, this enable comes, this timer comes, this Q out temp becomes 1. Okay, and my Q out temp 1 was actually 0. It was 0. Why it was 0? Because this was not set. The set had not come, and it was just reset. Okay, so it was having the value 0. So my Q out is on. It will be on. My this counter keeps running. Okay, this counter keeps running. until it reaches the value of n timer. Okay, once it reaches the value of n timer, it gets reset. Okay, it gets reset and it stays off. So it gets reset. What happens once it gets reset? This gets set. Okay, this gets set. This gets the value 1. This reset has happened. This gets set, and this counter starts running. So it starts running until it reaches the value of. Let me draw it better here. Okay, this was my n timer. Okay, once this has gone low, then the enable signal comes over here, and then this timer will start counting. Until it reaches the value of n minimum. Once it reaches the value of n minimum, it will again go. So this time is my t on. This time is my t off minimum. Then, okay, so after this time, both the timers have finished counting. Okay, and then it will continue to remain off. And then once an enable signal comes again over here, then my timer will again go on, and it will be high for minimum for this t on period. Okay, so any doubts in this?
Sir,
Mm-hmm.
sir, now, sir, can we discuss this Q out temp, Q out temp 1 and this Q out alone, sir?
Okay, you want Q out?
As a total of both the circuits,
Okay, total.
both
Okay.
constant on time and minimum off time.
Mm-hmm. All right, so
When the
okay, I'll draw with a different pen, then probably you can't be seen it. Let me make it green. Okay, so I'll just draw on top of this. Okay, it might be cramped up, but just bear with me. So
even about the diagram,
this will be my the green one. This Q out temp is given by green. Okay, this is given by green. Q out temp. Then go to the yellow. Q out temp 1 is given by yellow. So after this Q out temp is over, then my Q out temp 1 will come like this.
exactly not of that.
Yeah, it will be not of that. Wait a minute.
This color is not so visible, sir. Okay, no problem.
It is not visible, huh?
Not so visible this area. Okay.
One minute. Is it better?
Yes, sir.
So it will be like this. So Q out is the AND of Q out temp, that is this, and not of Q out temp 1. So if you see the logic of Q out, okay, Q out is Q out temp and wait, this will be Q out temp 1, Q out temp. Okay, that this is my truth table. Okay, that's why truth tables you should sort of think in these terms. So what is the truth table of this? Okay, if Q out temp is 0, if Q out temp is 0, Q out is 0. If Q out temp is 0 and Q out temp 1 is 1, still it will take the value of, wait, this has to be
0.
1. Still it will take the value of 0. Now Q out temp is 1, then we have to check Q out temp 1. Q out temp 1, if Q out temp 1 is 0, the not of Q out temp 1 is 1. So 1 and 1 will give you a value of 1. Next case is Q out temp has a value 1, but Q out temp 1 has a value of 1. Qr temp 1 has a value 1. So Qr temp 1 will go, not of Qr temp 1 will be the logic low. So logic low and logic high will give out the value of 0. Okay. So this is how Q out comes out. So if you see Q out, which is this one, this is Q out. It is Q out temp and it with not of Q out temp 1, and it will have this waveform. It will have this shape. Okay.
Sir, this P of min of Q out temp 1 we have drawn. This T of min, after that also it should extend. Okay, this is the minimum T of anyway.
Yeah.
Sir, after that T of min, in
after
that
T
Q
of
out waveform.
After T of min, Q out temp 1 will go to value 0. And we saw, no? If Q out temp 1 has a value 0.
Yeah. So this Q out will be 0.
No, Q out. Wait a minute. Q out temp. Wait. It is this case. Q out temp 1 has the value 0 and Q out temp also has the value 0. So the output comes to be 0. Okay. If you see, you're talking of this portion, right?
Yes, sir.
Yes. So in this case, both are 0, 0, 0, 0. So Q out also has the value 0.
Usually here we are using same circuit 2 times in a way that one drives the other.
Yes, in some sense. Oh, yeah, correct.
Completing person.
That way.
That triggers the circuit.
Okay. So I'll go to next thing. Okay, and this is again, this how you implement this, how this is generated. No, this is for n count minimum. This is a code for your free running counter. Okay, it's the same type of code that you have to implement, and this is assign. Okay, so this part of your code is for your free running counter. Now, and this line of code is for this, and Q finish comes from here. Okay, this is how Q finish comes.
Sir, here instead of writing, here we are instead writing if not of Q out temp 1. We can also write Q out temp 1 equal to 0, right? Here, both are equal to.
Where?
Here in the second line of code.
Yes. You can write that also. That's also a sequence. This actually might be a bit confusing for you guys, right?
Because here also there is a not in the circuit. Not yet.
Okay. This is just logic. Yeah. So you can write accordingly. So we'll proceed. So this is the code of your constant order modulator. Now we need to generate my enable signal. Okay, this is my enable signal is there. Okay. Now, what is QTR? You will ask, what is QTR? So we have my Vref and my Vout. Okay, they are coming. When my V output becomes greater than my Vref, then my QTR will be high. Okay. So as I drew the waveform, suppose this is my Vref. Okay, this is my Vout. So my QTR is this. Okay. This is my V output. This dash line is my Vref. This is my QTR. Okay. So my enable signal can come when this is high, when QTR goes high. That is one case. Or this is logic is for my minimum off time. Okay? This logic is for minimum off time. and this some external clock which is provided just as a fallback or extra safety precaution that by chance we are not able to turn on the circuit, then this possibility also is there. So what happens is
So this QTR should come only when V0 is greater than V, right? The moment at which
the moment that V output becomes less than Vref,
as per this op amp.
have I written it wrong? This should be plus, this should be minus. Sorry. Okay, whenever my V output becomes less than Vref, then my QTR goes high. Okay. So if my QTR has gone high, now assume in this condition, okay, in this case, this is my Vref, okay. Let's suppose there was some sort of load transient or something. Okay, this is my V output. Okay, and this is my QTR. My QTR will be 1. Okay, when this has gone high at the rising edge, okay, it's gone at the rising edge. This is my Q out. Okay, my Q out. It will go high. Okay, it will go high. It will be on for on time. Then it will be off for some minimum off time. Okay, and it will continue to remain off. It will continue to remain off. If it continues to remain off, what will happen? Your output voltage will keep on falling. Will keep on falling. But that is not what we want. Okay, that is not what we want. Why it is not? See, QTR is 1. Okay, my QTR is 1. That is sort of signifying to my circuit that my output voltage is falling. So I need to turn on the switch. I need to turn on the switch. But the issue is no edge is not coming. This edge, this rising edge, this edge is not coming over here. Okay, that edge is not coming. So it does not turn on. It does not turn on. So now we need to have an additional feature. What feature we have is after this TR is high, then your minimum off time is done. Okay, after that, we will generate a clock. That clock is known as my F minimum. F minimum. So my F minimum is 1. Okay, if there's a rising edge of the F minimum and QTR also is 1, then what will happen? Q minimum also will be 1. Okay, so when it is rising from 0 to 1, there will be an edge, and that will be used by enable to again trigger, and then my on time will start. Okay, then my on time will start. Okay, then my on time will start, and it will proceed. So after my minimum off time, even in case there is, what has happened is my output voltage is less than my Vref, and it means that I must turn on my MOSFET on my switch. But because my QTR no edge is coming, I am generating a logic of generating an edge. That is, after my off time is finished, I will raise a flag. Okay, I will raise this F external flag, F minimum flag, and that is ANDed with my QTR. F minimum is ANDed with QTR, and that edge, that positive edge is used to turn on my MOSFET again. Okay, turn on the MOSFET again for constant on-time control. Now, F external is another external clock that is coming at switching frequency. You saw FSW sir has generated. That is the clock for that. Okay, F external, and that is like an additional safety thing that in case this fails or this fails, and if it is still falling, your output is still continuously falling, then you need this F external is present. Okay. So any queries in this?
Sir.
Okay, so we proceed.
So this F external actually comes from where the clock.
You remember I told the ADC clock we showed.
Yeah.
Then also there was that FSW clock, okay, which was actually 100 by 200, 100 by 500 something. So that is the entitlement. Okay. It comes from there. Now we will go for edge detection. How do we detect the edge? So what we do is my input is Qn. Okay, this is my input. So this is my input Qn. All right. And at my F, and what is my Q1? Okay, suppose this was Q1, Q2, and F clock. My clock has come. Okay, clock has come. Q2, you assume Q1 to have the value 0. Q1 has the value 0. Q2 also has the value 0. My F clock will come. Q2 will be assigned a value of Q1. Since Q1 is 0, Q2 will continue to remain 0. And Q1 will be get assigned a value of Qn. Since Qn is 0, will continue to remain 0. So this will happen over another clock comes, another clock comes, another clock comes, etc. It will continue to remain like this. Then suppose a clock comes over here. Okay, clock comes over here. What will happen to Q2? It will take the value of Q1. So Q1 was 0, so it will hold on the value Q1. But Q1 will be assigned the value of Qn. So that will go high. Will go high. Then my next clock comes. Now Q2 will be assigned the value of Q1. So it will go high. And my Q1 will hold on to, will take the value Qn. So it will continue to remain high. So it will continue to remain high like this over here till here. It depends on your clock. Okay, when your clock comes. And then it will turn off. It will take the value, turn off. And this will be a delayed version of that. Okay, your Q2 is a delayed version of Q1. Then your Q3 is your XOR. Okay, your XOR of Qin and Q2. Okay, what is the truth table for XOR circuit? XOR circuit, just say Qn, Q2 is Q3 is 0, 0, 0, 1, 1, 0, 1, 1. So it will be 0, 0 when both are same, and it will be 1, 1 when they are opposite. So Q3 will be high. It will be high from here to here. When both are the same, it will be 0. And in this case, when both are different, it will go high. And in this case, it will go low. Okay? It will go low. Okay. Your Q edge. Your Q edge is given by Q3 and Qn. Okay, this is your Q edge. So when your Q3 is high, okay, when Q3 is high and Qn is high, your Q edge will come out to be high. Okay. And in this case over here, Qn is 0, this is 1. So still it will remain 0. So this is your Q edge. Okay. In this case, this is how you're generating the edge signal. So effectively, when your Qn goes high, you are generating a Q edge signal. Okay. Any queries in this?
Sir, here this XOR we are having a Q3 output, comma input. So here in these conditions there will be no delay. Here if
No, the delay is for the clock. This clock is generating
for
the
the,
delay.
only with the clock we are delayed. We are creating the delay. Okay. Here there will be instantaneous. Here there is no propagation delay or something.
Yeah. Propagation delay, no, we don't consider for these things. Okay. What is Qn? Where is Qn? Qn is my input. Okay, Qn is my input. So effectively the output of your edge detector, let us, the output of your edge detector is like this. Okay, this is my edge detector circuit. Okay, this is my Q in. The output is Q edge. Okay, so output of edge detector circuit will be like this. This will be your Q edge. So when it rises, it will give a short pulse. That is what is an edge detector circuit. And that is how we have written it in the code. Okay, in the code, you have written this edge detection logic.
So when it,
Sorry?
when it sees this, when it sees this QH pulse, then QTR will become 1.
Yeah, that is that. Yes, exactly. Okay, so the meeting will end in 1 minute. So I will start the next meeting. Yes, enjoy. So this is my logic for my edge detector circuit. Now we will go to the actual entire VMC model. Okay, how do we generate a gate pulse? So one more thing is this comparator status. Okay, this comparator, it has a status. It could either be 0 or it could be 1. So how are we writing that logic? If your VREF, okay, your VREF is greater than your ADC data. This is greater than this, then what should be the value? Should take the value 1. Your VREF is less than your ADC data, if you take the value 0. That is given here. Okay. And your PWM high is Q out and your PWM low is 0. In this case, we are considering discontinuous conduction mode. Okay, what is DCM is? Okay, so in this case, okay. This is my buck converter, okay. QH is your main switch, okay. This is your complementary switch. In the actual conventional buck converter, this is just a diode, okay. So if I do not give up S bar 1, if I do not make S bar 1, then it will just act like a diode, okay. It will just act like a diode. And this is done in light load conditions, okay. During light load conditions, we do that, okay. So that's why I do not require any dead time circuit over here. No dead time circuit is required. Not required. Because I'm giving only one pulse for main switch, the other switch is always off. It's always off and it will conduct to the body diode. So the current will conduct to the body diode. Okay. So that is the concept. And these are certain hardware results which Sir has shown. So this is on time, then it is off for so long. Further just going. Okay. So these are certain hardware results. This is the output voltage. This is the inductor current. So has demonstrated this also in the videos. Similarly, other cases, other scenarios by changing the input voltage. And this is a case where the minimum off time is coming. It is on, then it's off for some short duration, then it is on, and then it turns off, etc. like that. Okay, so this all have been shown. Now we will go to the current based constant on time control. Okay, current based. So till here, any doubts? Any
Converted
yes.
Yes, sir. In that light load condition, sir, when we are using diode, does the circuit itself will ensure that diode is turning on only after the switch is turned off?
Yeah, it will ensure. Okay, because the tended diode will be reverse biased, no? When
Yeah, but there will be no
when S
simultaneous
is
conduction.
no, it will not be there. Because when S is on, then your voltage which comes over here is Vn. Okay, that will reverse bias this. So it will not conduct. Then what happens when your switch is turned off? Okay, when your switch is turned off, your inductor current was still flowing. It is still flowing. So your inductor will develop such a voltage that the net voltage over here will be positive. It will be developed by your inductor because it has to force the inductor current to flow. And due to that developed voltage, this diode gets turned on
and it converts. Okay, so I'll proceed. Now we will go for current mode control using constant on time control. So previously we were just using Vref and V output. Okay, we were just considering Vref and V output. We were just considering. Now we are doing actual close. We are considering both your output voltage as well as your current signal which is there. And as you know, constant on time control is valley current mode control. Okay, valley current mode control. So what happens is, this is suppose your inductor current. Turns on. This is your valley reference. Okay, this is your I valley reference. So it was on for this time. Once it reaches this thing, then it will generate a trigger, and that will trigger your on time for a fixed on time that is still here, and then it starts turning off. Once it reaches this valley, then again it turns on. Yeah, again it turns on. So this is your logic for constant on time control. So it is valley current mode control. Okay. So it is similar. You have your output voltage pass through your output is sent from ADC, it's compared with your reference, error is generated, passes through your PI controller, and generates. From that, you have a current reference which generates your NP. That gets converted from your DAC to an analog signal that is compared with your inductor current, and based on your comparative status, that goes for your constant on time modulator. And then you insert dead time, etc. Because this could be for this is not for light load condition. This could be used for higher load conditions as well. Okay. So it is for that. So any doubts in this implementation? Okay. So if not, I proceed. So as I told over here, like this is my implementation. This is my inductor current, and this is my valley reference. And when it reaches my valley reference, then it gives a trigger to turn it on for a fixed duration. There's a minimum off time is there. The minimum off time is done. Okay, minimum off time is done. But still it does not reach my valley. So only once it reaches my valley at this point, then only it will trigger it to be on for a fixed duration. Then only it will trigger it to be on for a fixed duration. So this is the concept of current valley based constant on time current mode control. And these are certain experimental results. So if you will see, this is the valley current. Okay, this is the valley current, I valley. And that is set at 2 ampere. 1 ampere here, another 1 ampere here. That is why my current is always reaching this point and again turning on. Okay, it is always reaching the valley reference and turning on. Okay. And this is shown for different voltages. So if you would observe, there is no instability. It is always like this. Okay, it's like this, like this, like this, like this. It is not of the form like this, like this, like this, like this. So these are known as subharmonics. Okay. This happens in fixed frequency. When the frequency is fixed, because of the limited frequency and time available, such things happen. Okay. And then you need to add ramp, etc. You need to add ramp and all that. But that problem you do not face in variable frequency. In variable frequency, these stability issues are not there. Okay, this is for regarding the current loop. When you close the outer voltage loop, the stability issues also will be there. That is for both cases, but the actual inherent current loop is stable. Okay. And if you want to do constant off time peak current mode control, see, we talked about constant on time. In constant off time, how is the case? This is your peak. Okay. Then it remains off for some fixed duration. T off. Then it will be on.
until it reaches the peak. And once it reaches the peak, it triggers your off, and then it will remain off for a fixed duration. So this is your on time, T on. Capital letters say that it is a permanent fixed value. Small letters say that it's a variable quantity. Right? So your signal, your gate signal will be like this. Okay. So this will be fixed. T off will be fixed. This will be T on 2, T on 1. They will vary. Okay. And then because it is constant off time control, it is peak current mode control. Okay. It is peak. Once it reaches the peak, then it will trigger the off time, fixed off time. Okay. And then once the off time is completed, then it will turn on then it will be high for a duration until it reaches the peak. Once it touches the peak, it will again be turned off for a fixed duration. So this is the concept of constant off time peak current mode control. Okay. And the FPGA implementation is similar.
What is
Sir,
like if the input is changed in constant on time or off time, input voltage is changed, what is the effect on the switching frequency and inductor ripple current?
I'm not able to exactly recall. It is sir has showed some expressions, right? So based on those expressions, if your input voltage changes, your frequency would change, etc. Those stuffs are there.
Oh.
That's why we go to adaptive one time also. We'll try to complete that. Okay. Yeah. But
Sir, one thing you have mentioned is like in this limited switching frequency, like the waveforms changes, and here you don't have that constant. Could you please elaborate that point?
Yes. So what happens here is once it is constant on time, right? It has reached this value. Then for it to reach the valley, it has a lot of time. Okay? It has a lot of time. Like this time, this T off can vary. It can vary. Okay, there's no constraint on this. But in this case, because my time duration is fixed, okay, this my time duration is fixed. This is my on time. Okay, suppose let us consider peak current mode control. It was on, it comes over here, it reaches a peak, and then it is turned off. We would like it to continue to go on down, but because it is fixed frequency, another set pulse comes and again starts rising. It again starts rising. And because it has not fallen much, when it rises, it quickly reaches the peak and then you turn off. Then again, after a duration of T, I am again giving the pulse. If it again turns on and this will proceed. So this is a problem with fixed frequency, is like there is a constraint on the time duration available for it to reach, so that it doesn't have that, that steady periodic behavior. Is limited. There are certain constraints on that. All right. And this is a well-known fact for peak current control. The duty ratio is greater than 0.5, then it is unstable. Similarly, for valley current mode control, the duty ratio is less than 0.5, it is unstable. This for fixed frequency. But for variable frequency, that difficulty is not there. But the disadvantage is the frequency will vary. Okay,
Sir,
so then,
in case of peak CMC or valley CMC, like there is a ramp compensation technique, right?
Yes, ramp compensation can be applied. But
does it has certain limitations? After some duty ratio, even the ramp compensation also becomes unstable?
No. Yes, that depends on your ramp. Okay. What, like sir has demonstrated, your ramp, you can add ramp. Okay. Some value of ramp you add. Suppose you add ramp of slope 1. Slope of 1. Then it might be stable from 0 to 0.6 duty ratio. Okay, it would be stable in that. Further than that, it would be unstable. Suppose you add a ramp of slope 10, assume. Then it could be stable between 0 to 1 also, it could be stable. But what happens is when you add a ramp, you're slowing down your system. You're slowing it down. Then the advantage, so your current mode control effectively, it loses its effectiveness and it becomes into voltage mode control. So that is not always desired. Okay. So we
Slowing
cannot.
CMC means
What are all?
slowing down a CMC.
The speed, the ramp, it slows down the system, slows down your closed loop. Okay, that is why uh, the bandwidth of the system is reduced, and when the bandwidth of the system is reduced, how fast it can respond will reduce. And so, as you increase the slope of your ramp, it will soon effectively start behaving as voltage mode control, even though you are having additional components and architecture for doing current mode control. It is effectively behaving as voltage mode control. Okay.
Okay.
Right.
Sir, in this fixed frequency, there will be a limitation on switching frequency, right? To get it stable.
No, fixed frequency is, what do you mean limitation of frequency? Fixed frequency, the frequency is fixed. It doesn't change. What do you mean by stable and all that?
Sorry. This is a inductor current, right?
Yeah, inductor current, yes, exactly.
Sir, if we keep the switching frequency to below a certain value, then this unstableness can be solved, right?
Can't say that actually. See, all this depends on your input voltage. Depends on your input and output voltage. On the slopes, it depends on your slopes. Okay, it depends on your slope. If you have known some M1 by M2 slope should be less than 0.5 or something is there. Okay, some expressions are there. So it depends on the slope. It does not depend on the frequency. And this M1 and M2 slope depend on your input voltage and your output voltage. Okay. So I think I have done some of these slides. I don't know. There is a second case study. So we will go to that. Okay, we will go to those case studies. Sure. Similarly, using constant on-time modulator block and these comparators, you can also implement constant off time. Okay, you can also implement constant off time. So you just have to make certain inversion, etc. Here in the constant on time, this was a knot was there, but now this knot is not there. So you can easily transition from constant on time. Actually, I refer it to fixed off time. Okay, because you can't have COT, you cannot say for both constant on time and constant off time. So constant on time, COT, and FOT stands for fixed off time. Okay, like that is my way for remembering myself, and some papers use refer it as FOT. Okay. So these are some experimental results are there. So now we will compare. Okay, like mixed signal peak current mode control, and this is the architecture for constant on-time peak current control, and this is the architecture for constant on-time current mode control. This is the implementation diagram. Okay, yes. So this is peak current mode control with ramp, right? My input voltage is 2.5. My output voltage will be 1 volt. This is my load resistance, and this is my reference. 3.5 ampere is my peak reference. 2 ampere is my valley reference. Okay. For constant on time, I need a valley current mode control, so that is 2 ampere. For constant off time, I need a peak reference. It is 3.4 ampere. For peak current mode control with ramp, also I need a peak reference. That is again 3.4 ampere. So my input voltage is 2.5 volt. Okay. If my V in is 2.5, my V output is 1 volt, then my duty ratio is 1 upon 2.5. That comes out to be what? It comes out to be 0.4. Okay, my duty ratio is 0.4. So it is stable. It is stable. All of them, you see, they are stable. Now I'll go to the next case. I have gone to input voltage of 2.25. Input voltage of 2.25. So now my duty ratio in this is 0.444. Okay. 0.4444. Still, in both cases, it is stable. In both cases, it is stable. These have to be stable. These will always be stable. But this will slowly start showing instability. Okay. Now we'll go to the next case. Yeah, over here you will see. Now my duty ratio is 1/2. That is 0.5. Okay. I have also added ramp. And theoretically, by theoretical means, in peak current mode control, as long as my duty ratio is less than or equal to 0.5, it should be stable. But here it is showing unstable. Okay, it's showing unstable. And to stabilize it, I need to add a ramp. Okay, you need to add a ramp. So a ramp has been added. A ramp has been added. But the slope of the ramp added was low. The slope of the ramp added was small. It was not that large. And due to that, even though ramp was added, it is unstable. Okay, it is unstable. Whereas your constant off time, your constant on time, they are stable always. They are stable. So I am keeping on changing my input voltage and output voltage. They are continuously remaining stable. But what will change over here, you will see the switching frequency has increased. The effective switching frequency has increased. In this case, my effective switching frequency has reduced. Okay. In this case, my switching frequency will remain same, but there is instability added. Okay. And so any doubts in this?
Sir, like ramp compensation, from valley it is estimated or from peak it is estimated, sir. Are we compensating with the positive ramp or negative ramp?
You will actually, to peak current mode control effectively, what you're doing is this is your peak. Okay. This is your peak. This is your original I reference. Okay, your current would originally hit over here and would fall. But when we add ramp, we are changing the reference, we are subtracting the ramp from your reference, and your new waveform it will be of this form. You come here and it will start falling. Okay, it will fall at a earlier instant. Okay, it will sort of like it is reducing your duty ratio, etc. So that way it will stabilize it. Okay, this is your ramp. If you actually, I have given a nice document. I have actually added it in last week's video in YouTube for peak current control and reference document is there. Peak current mode control reference document by ST Microelectronics. So
Okay.
there you can understand. There they have explained how to do it. Like
Okay, sir. But actually, there are two compensations, right? Like either the positive slope can be added.
No, you either
or
yeah, there are two positions in the implementation architecture where you can add the compensation. Okay, that those are available for you. You can either subtract it from the, you can either add it to the inductor current or you can either subtract it from your reference voltage. Okay, so from your reference current, two things are there. But to add it to your, like you, it depends. In that SCM document, if I'm not mistaken, you're subtracting it from your reference actually. Okay, so that document is regarding to the microcontroller, how they do peak current control in microcontroller. The document is there. So,
sir, in your channel only the videos are there. These documents.
it's there, no, it's actually there. Yeah. He's saying it's there actually. Sanjay is saying. The link is there to those documents. The link has been attached.
Where, sir? On the comment section or where?
No, the actual section. You go on, let us see this video. See this video. Over here, there are links. Okay, the folder to access nodes, all that is there. Right. So in this one, I think I will put it over here.
Yeah, that takes to that NPTEL
Yeah. Over
given.
here. This is the document I'm referring to. STM32, what current control. Right. So this has the how these are the waveforms. Okay, UWM signal. How, where, and all, which is a set reset. Okay, this document is very useful. How it is there. Then how these disturbances, the subharmonics are coming. How you can add the ramp, which is ramp should be there. Okay. Ramp thing was there. Slope compensation. Okay, how do you add a slope? How do you calculate the slope? All that is there. How do you design the gains? How do you design the controller? All that has been explained over here. Okay. In the implementation of that in microcontroller. Over here. All that has been shown. So you can refer to this document, it has been shown. Yeah, yes, you're correct, Samir. That stability issues for fixed frequency and for variable frequency, there are no stability issues. Yes. Okay. All right. So you can check this document. It was very useful for me. You can also try to understand it. All right. So this is what I mean, that this is your, okay, I can't edit it. I can't write on it. This. You have your peak reference over here and you're subtracting this. This is your new reference. This is your new reference. I ref new. So from your peak reference, you're subtracting, you're adding a negative slope, and that is your new reference. Right? So that is your peak current mode continuing with the ramp compensation.
But is this ramp compensation is same as that emulated ramp concept, or it is different?
No. This is different. This is different. Emulated ramp is internal. It's internal inside FPGA. That is for fully digital current mode control.
Okay. Okay. I'm thought both are same.
No, they are not actually. Okay. So these are certain expressions of how the frequency varies. It is fixed for fixed frequency, constant on time. It depends as the input voltage is reduced, your frequency increases, and that is a disadvantage. That is slightly problematic. So that's why we have adaptive on time. Adaptive on time is a concept is there. We use that. Similarly, for constant off time, highest switching frequency at highest input voltage. So if you have noticed, I showed, right? For constant on time, as your input voltage is reducing, the input voltage is reducing, the switching frequency has increased. But for fixed off time, as your input voltage was reducing, your switching frequency was reducing. Okay, so that is actually shown over here. From these expressions, you can see. Okay, then now now we will consider light load. You see your mobile. If you assume your mobile, you have a mobile with you. If you don't have severe mobile addiction, then possibly most of the time your mobile is.
Sir, your audio is not clear.
Now is it clear? Hello?
It is clear only, sir.
Okay. So, like, what I mean to say is like a mobile.
No, sir, not clear.
Others are saying clear. Both the other students are saying clear. Maybe it's your.
Is it only for me or anything else?
Only for you. Only for you. It's coming. It's happening only for you. Okay. Sure. Okay. So, in most cases, your
converter or like your back.
Sir, what is the concept of light load? Sir, could you please explain it?
Yes, light load. Yes, that's what I'm saying. Your mobile. Okay, you have a mobile. So if you're seeing a movie, it is, and you're seeing movie, you're listening to songs. Okay, all these things are happening. Then your processor, your mobile processor, etc., they will draw lots of currents. We'll just take a figure of 10 amperes. Okay, and but now suppose you're sleeping. Okay, you're sleeping. Then how much current it will draw? Your processor will draw around like 0.1 ampere, etc. Just standby mode. Okay, it's like a standby mode. Just some amount of very small amount of current for keeping the circuit power, the clocks and all, timers, all those to be on. That is your, it's on standby mode. So, but still it will draw very light current. And in most of the cases, you're not using a mobile, right? Your mobile should be active enough to receive the call, okay, or to get the notification, etc. But it will not be consuming lots of power. So it is like in standby mode. That is light load condition. But when you are actually using your mobile to play a game, see movie, etc., you're seeing lots of stuff, then your mobile is full load condition and heavily loaded, and it draws a lot of current. Now we want our converter. Okay, this basically power electronics. We are generating a sort of converter. Okay, just like a power supply. It must be able to provide enough current. This much current it should be able to provide. All right, it should be able to provide, and that also that time the efficiency should be high. But in most cases, it's operating at 0.1 ampere. Very light load. Okay, very light load. Assume your output voltage is of 1 volt. Okay, so in this case, you're at heavy load, P out is 1 into 10 is 10 watt. But in light load condition, your P out is 1 into 0.1, that is 0.1 watt. Okay, this your output power is 0.1 watt. Now, if you want to have a high efficiency, you want your neta to be high. Okay, assume your switching loss is around 0. Let us take a very good number, 0.05 watt, and your conduction loss is around 0.01 watt. Okay, these are just figures I randomly made up. For heavy load, or heavily loaded condition, heavy load, what will be your efficiency? It will be 10 divided by 10 plus 0.05 plus 0.01. That comes out, this is a very fictitious figure. Comes out to be an efficiency of around 99.4%. But in light load, what is happening? Your efficiency is 0.1 upon 0.1 plus 0.05 plus 0.01. That comes out to 0.1 upon 0.16. That gives an efficiency of around 62.5%. So can you see the drastic reduction in the efficiency? Why it is happened? Because it is in light load condition. And that we do not want to happen. We want the efficiency to be high throughout. At light load, high load, etc. It should be high. And what actually is dominating is your switching loss. Your switching loss, okay, we have assumed the switching loss to be same. Okay, switching loss to remain same. In heavy, okay, your switching loss is the one which is dominating. And the switching loss is dependent on the frequency. So if I want to reduce the losses, what I have to do? I have to reduce my switching loss. And if I have to reduce my switching loss, what I have to do? I have to reduce my frequency. My switching frequency, I must reduce it. One more thing I forgot to mention is my conduction loss depends on my current. My conduction loss depends on my load current. Okay. So in this case, my conduction loss will be 0.01. But in light load case, you can assume my conduction loss will reduce. This is reduced by 100 times, so this also will reduce by 100 times. So like probably assume, so it will be like 0.01 divided by 100. My conduction loss is dependent on my load current, and my conduction loss will reduce at light load. That is fine. But my switching loss remains same.
if I'm operating at the same switching frequency, my switching loss is the same, irrespective of whether I'm operating at high load or light load. And that I do not want, because that is what is resulting in a reduction of my efficiency. So if I want to improve my efficiency, what I would require is I have to reduce my switching frequency. Okay. Yeah, so you can ask your doubts.
Nice explanation, sir.
So this is where like the switching losses dominates at higher switching frequency. And so we have to, now in this case, what we have to do, we have to reduce the frequency. So to reduce the frequency, we will go for light load control methods. Okay. One is pulse frequency modulation, PFM. Okay. This is pulse frequency modulation. In this, what happens? We are changing the frequency. See, pulse with modulation is what? Your frequency is the same. P is the same. Only the width, this width of the pulse you are changing. In pulse frequency modulation, what is happening is you are changing this time. This time t is variable. This time t is variable. This is pulse frequency modulation. Okay. So your on time can be fixed. Okay, your on time can be fixed. This can be fixed, but your t is variable. Okay, so this is like pulse frequency modulation. So constant on time control is a type of pulse frequency modulation technique. Okay, there's pulse skipping modulation also is there. And burst mode also is there, and hysteresis control also is there. Okay, these are various control techniques are there. Now this is DCM. Okay, in DCM, what happens? It is on, it turns off, and it remains off. Okay? For some time until the next pulse comes for it to turn on. The duty cycle in this case is a nonlinear function. It depends on input voltage, output voltage, and these various factors: output current, input voltage, etc. And this is your ripple. Okay, this is your output voltage ripple. These are all for buck converter. Remember, these are all for buck converter. Now, in constant on time, what happens is your switching frequency. Your switching frequency is dependent on your output current. Your switching frequency is directly dependent on your output current. So if my output current is reducing, okay, from 10 amperes it has gone to 0.1 ampere, then my switching frequency also will reduce. Accordingly, it will reduce. Okay. And this is advantageous because I want it to happen like that. So using constant on-time control, which is a variable frequency control method, it has the inherent property of this modulation technique that at high load conditions, the switching frequency is high, and as my load is reduced, my switching frequency will reduce. All right. And this is very advantageous, and that's why constant on-time control is very popular. Okay. So now we have established that constant on-time control is a pulse frequency modulation technique, which has the property that it depends on the load current, and if my load current reduces, my switching frequency also will reduce, and this is a very, very attractive feature. But there is a drawback. Your output voltage ripple depends on my input and output, etc. My on time is fixed. My on time is fixed. LNC is fixed. Output voltage also might be fixed, okay, because it is regulated. But if my input voltage changes, as my input voltage changes, my output voltage ripple will change. So we have found our output voltage ripple will change. Now that would not, there is a constraint. You have this limit that your output voltage ripple should be less than 1% of your output voltage, etc. Now what could happen is at certain input voltages, this constraint might get violated. Okay, it could get violated. So in case it is violated, then our design is not worked and we don't want it to violate. So for that, we have to come up with a technique known as adaptive on time. Okay. The pulse skipping and all, I'll skip it. Okay. This meeting will end. So I'll again start in the next meeting. So another thing I told that this DCM occurs at light load. It will usually occur at light load condition. So we have found this is the expression for voltage ripple. Someone saying something? And okay, and this is the expression for switching frequency remains same, but duty ratio changes. Okay, so these are certain expressions.
But how to get these expressions, sir? Like, where can we get all these derivations?
These derivations and all actually, I have to check where it would be available. These probably sir has taught in the previous NPTEL course. You could check over there. Okay, but it won't be very difficult for you to do. Actually, these are also many of my seniors' thesis, like they have worked on these things, so they are available like that. Okay.
Okay.
Yeah. So we established that so ripple voltage is increasing with increasing input voltage, and that we have to take that into account. And now we want to use this property that in constant term that the switching frequency is directly proportional to your output current over here. But this is something which is like a hindrance or roadblock, and we want to overcome that. So for that, we use adaptive on-time control. Okay. In that, how is the on-time being generated? Now, in this case, we are talking about it operating in DCM. Okay. We are considering it operating in DCM. So I have a fixed peak reference. Okay, my reference is fixed. So when my inductor current reaches this peak value, that is my on time. Okay, that is generating my on time. And this peak reference is kept like this. Okay. So if we consider this property and we know that T on is okay, these are expressions for T on, and we substitute that into the output voltage, we will get your output voltage ripple comes out to be in this fashion. All right. Your output voltage ripple it is dependent on I peak square. Okay. Your output voltage ripple L, C, and V output are you can say approximately same. They're approximately constant. They do not vary much. So your output voltage is directly proportional to the square of your peak. So if you fix your peak, then you're fixing your output voltage ripple. So that is the concept. I fixed this peak reference current, and then that's how I am fixing my output voltage ripple. I am fixing through that manner. Okay. So now, what do we do in this case? In the earlier case, you remember this is my minimum off time is the same as it was, and over here for constant off time there was this counter was there. Okay, free running counter etc. was here, and that was generating my on time. Okay, but in this case, I have this. When I have my peak reference, okay, my peak reference, my inductor current is starting from 0. It will touch. Once it touches, for that is my on time duration, and then it turns off. Okay, then it remains like this, and then again it will turn on. Okay, so this is how, using a fixed peak, I will be generating the same on time. Okay, my diagram is not correct, but your on time will remain fixed, but you're also limiting the peak. And why it is called adaptive on time is because when your input and output changes, your peak also will change. You will also change the peak based on that. Great, let us see the main diagram. Actually, it is not shown. These are the same. Okay, you'll see these hardware results. Okay, you'll see this hardware results. So over here, the peak, your peak is the same. Okay, and it's operating in DCM. Okay, your inductor current is 0. Okay, your inductor current is 0. So from here, it is reaching this value. It is reaching this reference of 1.2 ampere. So if you will observe, the on time in this case is fixed. Okay, there's some particular on time. Yet there's some T on 1. Now what has happened? My input voltage is 3.3. Now my input voltage is changed to 2.5. Okay, my input voltage is changed. But my peak reference remains the same. So I'm sorry, actually the peak reference remains the same. Peak reference now has changed to 2.5 volts. But my on time has changed to T on 2. Next, sorry, this is, sorry, peak reference is 1.2 ampere. Peak reference remains the same. Okay, peak reference remains the same, 1.2 ampere. But my on time is changed. So based on my input voltage, the on time gets automatically adapted such that my output voltage ripple, delta V output, remains within limits. Okay, delta V output remains within limits. So, any doubts in this? So if you have no doubts, we can end it.
Sir,
Tell them.
sir, at light load, the switching frequency can be increased simultaneously. This output voltage can also be within the limits.
Right. At
By
light load,
adaptive.
I'm reducing the switching frequency.
Ah.
I'm reducing the switching frequency, but also I'm simultaneously maintaining the output voltage ripple. The output voltage ripple I'm maintaining. So this is one method. This is one method of implementing it. There could be other different methods of adapting the on time. There are other methods as well, but this is one method which Suresh demonstrated. Right. So this is your effective time period. This is my effective time period. You are saying something?
It's a step change in the load.
Suppose
At that time, then switching frequency will also be having a sudden change.
okay. So whenever there's a step change in the load, the switching frequency has to change. Yes, because the load current has changed. Yes. Okay. So
Sir, at that time, how will this I peak be maintained, sir? So this this is independent of that load current. So I'm asking how
yes,
this
yes,
del
yes,
V
yes,
naught
yeah,
is
okay, I understood your question. So you're saying, see your load current, if you see your load current is approximately like this. This is the average value of your load current. Okay. This is your load current average value, load value. So, let me draw. Okay. This is your I load 1. Now you want to increase the load current. You make it, suppose you make it I load 2. What will it will reach this peak? This peak will remain fixed. Okay. This peak remains fixed. Come here, it will fall. Okay, the voltage remains the same, but it will turn on faster.
Yes, yes, exactly, yes. Yes, tell.
Sir, again, sir, at that time, this IP depends only on output voltage, right?
Yes.
That is,
See, this is specifically for considering that it will operate in DCM. Okay, your application is that it's operating in DCM, and based on your load condition, your switching frequency. See, if you see over here, your time period is more. Okay, so your switching frequency is low. In this case, your time period is small, so your switching frequency is high. Okay, this is the concept.
sir, our time period is small, but this on time is reduced now. Sorry, in the second case, I must increase.
Uh, mm, so effectively, your on time is adapted. Okay, your on time is adapted, right? Is adapted. I didn't say that on in adaptive on time, your on time will change based on your operating conditions. It will change based on your operating conditions. Okay. But at one operating point, the on time will remain fixed.
Sir, actually, to adapt, if you delve not within the band, if the on time increases, then V in has to be sufficiently has to vary accordingly to keep del V not within the range.
Why VN is coming into picture? See,
because del V not is having T on by V in, something like that. V in minus V naught. Then that equation will be.
oh, this is the expression, del V naught. It comes approximately like this. There's no V in here.
So here we are maintaining this IP constant.
Yeah, we maintain IP constant.
Yeah, but sir, for maintaining that IP constant, there should be a corresponding variation between T on and V in. Here, as per this equation, the second one.
This equation?
No, sir, on the left, this T on
No,
equal to
yes. So
to peak.
So how? So what? Let me like my point is your del V naught is fixed. Okay, del V naught is fixed. For that you have a fixed IP. Your T on will adapt. It will adapt based on the operating condition. Okay, if it goes from 0.1 ampere to 1 ampere, this will have a T on 1, this will have a T on 2. But when it is at 1 ampere, your on time will remain at T on 2. When it is at 0.1 ampere, your on time will remain at T on 1. So it is constant on time at that operating condition. Okay. But when your operating point has changed, then your on time is adapted. Okay. All right.
So that is what my question is. Sir, on time is adapting by changing V in only, no?
Yes, it will change. Yes, correct.
On time is adapting to the new
yes.
value by changing V in only.
Change in VN is causing a change in your on time. Yes. See,
So that adaptation will happen when the input voltage changes.
Yes.
We are trying to keep a del V not constant, a del V not within the range.
Yes, correct.
Sir, suppose the question is when the load current changes, then there is a step change in load current.
Yes.
Then how that load current will be change in load current will be changing as Vn, Vin,
No, it will not
so that the
affect me.
adaptation will happen.
No, no, no.
Yeah, it will not adapt.
No. Okay, so
And how this T-on will happen?
you are saying your output, you are saying your output current change in your delta I naught will result in change in delta Vn. Okay, that is your question, right? That is not in my hand, right? Sorry.
Okay.
See, because you see a buck converter. You see a buck converter, it's circuit diagram. Let's see. This is your buck converter, right? This can change. What do you mean by I not changing? What do you mean by delta I not changing? It means your resistance has changed. Your resistance has changed. That does not mean
Yes.
your input will change. Okay, that does not mean your input will change,
Yeah,
right? Input will remain fixed.
sir, but
Okay,
yeah,
now
sir,
we're talking.
but the
Yes.
but that IPG is maintained constant by making
No.
T on and V in change.
No.
Change between V in and T naught is the one which is making IP to be constant. If the load current changes, then
See, assume in this case,
IP doesn't.
load current changes, your IP will not change.
Yeah.
If your load current changes, assume your Vn is fixed. Okay, your output also is fixed. What has happened? Your load current only has changed. If your load current was earlier 0.1 ampere, now it has become 0.5 ampere. What is your load current? Your load current is the average value of your inductor. Your load current for a buck converter, it is the average value of your inductor current. In this case, it will be 1 upon T. This is your T. Okay, 1 upon T integration of this. Okay, this one. So it will be the area under this curve. Okay, that will be your area under this curve. That area, you assume that area to be A1. Okay, A1 upon T. That is your A1 upon T1. Okay, A1 upon T1. That is your I load 1. Okay, load current 1. That it says, let us say it has this value over here. Okay, that I've proved. Now, my load current has changed to I load 2. It has changed to I load 2. Okay. Now, this slope M1 for buck converter, slope M1 is V in minus V output. Slope M2 is V output. So there would be some momentary change in V output, okay, because there's a load transient. So when the load is increased, your output will reduce. All that is there. But then the closed loop will operate to regulate your output voltage to remain fixed. That we are not showing over here. We are now discussing about the steady state. Now, in the steady state, all right, in your steady state, your V in and V output have come to its steady, your V in is fixed, your output also has reached now its steady state value, its regulated value of 1 volt, assume. Okay, so this slope will remain the same. So in load 2 condition, what will happen? It will also be like this. It will be like this. It will be like this. Okay. This will be this much. Then again it will rise and it will fall. This area will remain the same. So for I load 2, what has happened is area A2, which comes, is actually equal to A1. Okay. Suppose this A2 upon T2. Okay. Your A2 is equal to A1. So I load 2 and I load 1, your area under the curve, does not change because V in and V output remain same. But the time period changes. The time period is the one which makes a difference. Okay. That's all. Yeah.
So that time also T on is constant.
That time also T on is constant. Okay. So any other queries? Okay, if there are no other queries, we can end the meeting now for today.
That's it.
Okay, thank you. Bye.